Tesla says its next-generation drive unit will use a permanent magnet motor with zero rare earth elements. If that claim holds, it could cut exposure to some of the most expensive and politically sensitive materials in electric vehicles. The mystery is that Tesla has not shown the full engineering. We know the target: lower cost, high efficiency, and fewer supply chain risks. What we do not know is whether this is a true motor breakthrough, a clever redesign using known technology, or a carefully framed announcement. That matters far beyond Tesla. BYD, Hyundai, Toyota, and every major automaker are fighting for cheaper electric vehicles. The biggest shock may be what Tesla is trying to remove entirely. 2023 Investor Day, the company made one very specific claim. Its next-generation drive unit would use a permanent magnet motor with zero rare earth elements. That statement appeared in a public presentation about Tesla's future vehicle platform, lower manufacturing cost, and simpler supply chains. This is important because the announcement was not a leaked laboratory result, and it was not a hidden patent suddenly discovered online. Put the claim in front of investors, analysts, and the public as part of its plan to build cheaper electric vehicles at much larger scale. Here is where the confusion starts. Tesla did not say it had invented a new kind of physics. It did not reveal the full motor architecture. It did not show the magnet chemistry. It did not publish torque figures, efficiency data, weight, thermal limits, or a launch date. He showed the direction, not the complete machine. That missing detail created a vacuum, and the internet filled it quickly. Some people described it as a finished engine, ready to destroy the competition. Others assumed Tesla had already solved every rare earth supply problem in the industry. Neither claim is proven by what Tesla actually presented. The verified announcement is narrower, but still serious. Its future permanent magnet drive unit would eliminate rare earth elements while supporting the company's goal of cutting cost and scaling production. If delivered, that would be a major shift in how high-volume electric motors are sourced and designed. So the real question is not whether a secret engine has been exposed. The question is more interesting. If Tesla gave so few technical details, why did one sentence shake the electric vehicle conversation so hard? Motor has one basic job: take energy stored in the battery and turn it into motion at the wheels. The better it does that job, the less energy the car wastes on every acceleration, every hill, and every mile of highway driving. In a gasoline car, the engine throws away a huge amount of energy as heat. Electric motors are far more efficient, which is why electric vehicles can feel so responsive while using less energy overall. Efficient does not mean perfect. Even a very good motor still loses energy inside the system. Some losses come from electrical resistance. As current moves through copper windings, part of that energy becomes heat instead of torque. Some losses come from magnetic behavior inside the steel and magnets. Some come from friction in bearings and gears. Then the cooling system has to deal with the heat, which can add weight, complexity, and its own energy demand. Because range is not determined by battery size alone. Two vehicles can carry similar battery packs, but if one drive unit wastes less energy, it can travel farther from the same stored power. That difference may be small on paper, but across thousands of miles, small efficiency gains become real money, real range, and less stress on the hardware. A more efficient motor can also change the economics of the vehicle. Needs less energy to deliver the same performance. The manufacturer may be able to use a smaller battery for the same target range. Since the battery is one of the most expensive parts of an electric vehicle, even modest savings can matter at scale. Heat is another part of the story. A motor that runs cooler can maintain performance more consistently, put less strain on insulation and electronics, and potentially improve long-term durability. Important in high-speed driving, towing, repeated acceleration, or hot climates. That is why Tesla's motor claim matters beyond headline performance. Modern electric motors are already highly efficient, so the next battle is not just about making them faster. It is about building them with better materials, simpler supply chains, and manufacturing methods that can scale. starts inside the motor itself. Many high-performance electric vehicles use permanent magnet motors because they can deliver strong torque, high efficiency, and compact packaging. Those magnets are not ordinary refrigerator magnets. In many designs, they rely on rare earth elements such as neodymium and sometimes dysprosium or terbium to stay powerful under heat and stress. It's a problem much bigger than one automaker. Rare earths are not always rare in the ground, but the mining, refining, and magnet manufacturing chain is difficult to build, expensive to regulate, and heavily concentrated. China plays a dominant global role, especially in processing and magnet production, which means the industry depends on a supply chain that is not evenly distributed around the world. Makers. That concentration turns a motor material into a strategic risk. If prices spike, a company cannot easily redesign a drive unit overnight. If export rules change, production plans can be disrupted. If political tension rises, a material buried deep inside the motor can suddenly become a boardroom problem. There is also an environmental side. Mining and separation can create waste, chemical pollution, and land damage when handled poorly. Automakers selling electric vehicles as a cleaner future have to think beyond tailpipe emissions because the materials going into the car matter too. This is why removing rare earths from a motor would matter beyond a single Tesla announcement. Reduce exposure to volatile prices, loosen dependence on concentrated processing hubs, and make large-scale electric vehicle production less vulnerable to geopolitical pressure. The challenge is that permanent magnets became popular for a reason. They help motors stay efficient, compact, and powerful across real driving conditions. So Tesla's claim sounds simple on the surface: no rare earths. The hard part is proving that a new motor can keep the performance advantages without the materials that helped create them. Engineering paths Tesla could be pointing toward, and none of them are simple drop-in swaps. One route is changing the magnet material itself. Instead of neodymium-based magnets, a motor could use ferrite magnets, which are cheap and widely available. The problem is that ferrites are much weaker, so the motor usually needs more magnet volume, a different rotor shape, or higher speed operation to make up the difference. Packaging, weight, and cooling. Another option is an induction motor, the type Tesla used in earlier Model S drive units. Induction motors do not need permanent magnets in the rotor. They create magnetic fields through electric current instead. The upside is material independence. The downside is that they often give up some efficiency, especially in everyday partial load driving, where permanent magnet motors are very strong. Is an externally excited synchronous motor. In this design, the rotor field comes from electricity fed into the rotor, not from permanent magnets. Several automakers have explored this because it avoids rare earths while keeping strong controllability, but it adds hardware, control complexity, and potential durability challenges because the system has to deliver power into a spinning component reliably. Also could be using a hybrid architecture that does not fit neatly into one category. Advanced rotor geometry, new winding layouts, higher voltage electronics, improved cooling, and smarter software can all help recover performance that weaker or different magnetic materials might lose. The important detail is what Tesla did and did not say. Tesla specifically claimed a rare earth-free permanent magnet drive unit. The company was not simply returning to a standard induction motor, but Tesla did not publicly explain the material formula, the rotor design, or the manufacturing method behind it. So the mystery is not whether rare earth-free motors are possible. They are. The harder question is whether Tesla can make one compact, efficient, durable, and cheap enough for millions of vehicles. That is where the real breakthrough may be hiding. Why the motor claim matters most when you connect it to Tesla's next-generation vehicle platform. The target is not just a better drive unit. The target is a vehicle that needs fewer parts, less factory space, fewer expensive materials, and fewer labor steps to build. A rare earth-free permanent magnet motor could help Tesla attack cost at the supply chain level. Materials are not just expensive. They can be politically sensitive, price volatile, and hard to secure at massive scale. If Tesla can replace them with more common materials, it reduces exposure to one of the most constrained parts of the electric vehicle supply chain. The manufacturing benefit could be just as important as the material saving. Designed for simpler assembly, can reduce the number of precision steps inside the drive unit line. Better thermal design can cut down on complicated cooling hardware. Shared components across multiple models can let Tesla buy larger volumes of the same parts, instead of creating a different drive unit for every vehicle. This fits Tesla's broader factory strategy. Repeatedly tried to remove complexity from the product so the factory can move faster. Giga castings reduced body assembly steps. Structural battery packs changed how the floor of the vehicle is built. A cheaper, simpler motor would push that same idea deeper into the powertrain. Tesla also has an advantage that most automakers cannot copy quickly. Software, inverter, battery pack, motor design, vehicle packaging, and much of the manufacturing automation. That means Tesla can optimize the whole system together, instead of treating the motor like a separate box bought from a supplier. So the real question is not whether this motor wins a drag race. The question is whether it helps Tesla build the next vehicle with less cost, less risk, and less factory space. If Tesla pulls that off, competitors are not just fighting a motor, they are fighting a cost structure. Structure is exactly why BYD cannot ignore Tesla's motor direction. BYD is not just another electric vehicle maker. It is a battery giant, a vehicle manufacturer, and a supply chain machine all at once. It builds its own blade batteries, produces many core components in-house, and uses enormous scale to push prices lower in China and overseas. That makes BYD dangerous because it competes where Tesla's next platform is supposed to matter most: affordability. Moves rare earth materials and simplifies the drive unit. It is attacking one of the few areas where BYD already has a structural advantage. BYD can pressure the market with price. Tesla is trying to answer with engineering and manufacturing efficiency. Hyundai is a different kind of threat. The Hyundai Motor Group has built one of the strongest electric vehicle platforms outside China, especially with its eGMP architecture. Ioniq 6 proved that fast charging, efficient packaging, and strong software integration are no longer exclusive to Tesla. Hyundai also moves globally, with factories, partnerships, and models designed for very different markets. For Hyundai, a Tesla motor breakthrough would raise the bar on efficiency and cost at the same time. Fast charging gets attention, but motor efficiency affects range, battery size, heat management, and vehicle price. An edge there. Hyundai cannot answer with charging speed alone. Toyota has a different challenge. It built its reputation on hybrid systems, durable motors, and disciplined manufacturing. It also has deep battery research, including solid-state development. But its move into full electric vehicles has been slower than investors and governments expected. A major Tesla motor shift would increase pressure on Toyota to turn research into production faster. Are watching for the same reason. Renault, General Motors, Mercedes-Benz, and suppliers across Europe and Asia are already studying motors that reduce or eliminate rare earth dependence. The question is no longer whether electric motors can improve. The question is who reaches low cost, high volume, and secure materials first. And that leads to the most important question of all. Is Tesla leading the next motor era, or is it responding to rivals that are already experimenting with magnet-free designs? Not walking into an empty field. Magnet-free and reduced rare earth motors have been studied for years by automakers, suppliers, universities, and industrial motor companies because the pressure is obvious. Rare earth magnets are expensive, politically sensitive, and difficult to source cleanly at global scale. One of the most important alternatives is the externally excited synchronous motor. Instead of using permanent magnets in the rotor, it creates the rotor's magnetic field with electricity. neodymium or dysprosium magnets are needed inside the spinning core. Renault has used this approach in production electric vehicles, and suppliers like Valeo and Mahle have pushed their own versions, including designs that try to reduce wear, improve efficiency, and simplify the electrical transfer into the rotor. BMW has also leaned heavily on externally excited motors in some of its electric drive units. The logic is not just about materials. Magnetic field electronically, the car can tune the motor behavior depending on speed, load, and efficiency needs. That gives engineers more control, but it also adds complexity because the system must manage extra current, heat, packaging, and long-term durability. There are other paths too. Some companies are exploring induction motors, switched reluctance motors, ferrite magnet motors, and hybrid designs that use fewer rare earth materials rather than none at all. Trade-offs. Induction motors can be robust, but often lose efficiency in certain driving conditions. Switched reluctance motors can be simple and cheap, but they can create noise, vibration, and torque ripple if the control system is not excellent. This is where Tesla's real advantage may be misunderstood. The breakthrough may not be that Tesla invented the idea of removing rare earths. The advantage would be making that idea cheap, efficient, quiet, durable, and manufacturable in millions of vehicles. A different achievement. Before any magnet-free Tesla motor becomes a mass-market weapon, it has to survive the boring tests that decide everything. It must handle summer heat, winter cold, high-speed driving, stop-and-go traffic, towing loads, water exposure, road salt, and years of vibration. Cooling has to be consistent. Noise must stay low. Maintenance cannot increase. Suppliers must prove the materials are available. Factories must build the motors with high yield, or the cost advantage disappears. Race is not a miracle story. It is a manufacturing story. If Tesla can combine motor design, power electronics, software control, and factory scale better than rivals, the payoff could extend beyond future cars. The same lessons could feed Cybercab, humanoid robots, factory automation, and a wider machine ecosystem where every watt, gram, and dollar matters. Moves this motor at scale, the biggest impact may be price. A cheaper, efficient, rare earth-free drive unit could support lower-cost cars, improve Cybercab margins, and carry into robotics where actuators need tight control and low cost. Exposure to constrained materials and make the supply chain harder to disrupt. But the proof still has to come from specs, production vehicles, cost data, and reliability results. If this motor becomes real at scale, will it be remembered as a technical upgrade or the moment electric vehicle economics changed?